In the last presentation, we looked at latches. These serve as the basic building blocks of flip-flops. In this presentation, we'll look at flip-flops themselves. A flip-flop is a binary storage device capable of storing one bit of information and having timing characteristics. In recalling latches, latches are basic storage elements that operate with signal levels, rather than signal transitions. They are level-sensitive devices, which are useful for the design of asynchronous sequential circuits. They generally have two inputs and one output pin. So there are some critical differences between latches and flip-flops. In comparing the two technologies, latches are faster and consume less power. Their main drawback is that they're asynchronous and not tied to the clock cycle, which is why we usually go with flip-flops. Change in value on the control input allows the state of a latch and a flip-flop to switch. This change is called a trigger and enables the flip-flop. The D latch with clock pulses on its control input is triggered every time a pulse to logic level 1 occurs. As long as the pulse remains active or at level 1, any change in the data input will change the state of the latch. The latch is transparent since its input value can be seen from the outputs while the control input is 1. This is a block diagram of a synchronous sequential circuit from our introductory discussion. You can see a feedback path from the outputs of the flip-flops to the combination circuit. The data inputs of the flip-flops are derived in part from the outputs of the same and other flip-flops. If we use latches for storage elements, serious difficulty arises. The state transition of the latches starts as soon as the clock pulse changes to logic level 1. The new state of the latch may appear as its output while the pulse is still active. The final state depends on how long the clock pulse stays at level 1. So the result is unpredictable and the situation becomes unreliable. Enter flip-flops, which are circuits constructed in such a way as to make them operate properly when they are part of a sequential circuit that employs a single clock. The key to the proper operation of flip-flops is to prevent them from being transparent. In a flip-flop, before an output can change, the path from its inputs to its outputs is broken, so a flip-flop cannot see the change of its output or the outputs of other similar flip-flops at its input during the same clock pulse. Thus, the new state of the flip-flop depends only on the immediate preceding state. This figure shows how we can create a flip-flop by connecting two latches. This is often referred to as a master-slave flip-flop, which has been the traditional term even though some people are now taking issue with it. If it's helpful, you can think of it as a leader-follower flip-flop, or I'll let you substitute whatever language is convenient for you while we wait for an official word and renaming. The left latch is the master and changes its value upon input when the clock is high. The value gets transferred to the right latch when the clock changes to low. Depending on the type of latch used to construct the flip-flop, there are two possible ways the flip-flop can respond to changes in the clock. One way is to combine the two latches such that the inputs presented to the flip-flop when the clock pulse is present control its state, and the state of the flip-flop changes only when a clock pulse is not present. Such a circuit is called a pulse-triggered flip-flop. A flip-flop constructed with SR latches is a pulse-triggered flip-flop, because changes on either the S or R inputs to the sample latch during the clock pulse can change the sample latch's output value. Thus, an SR flip-flop depends on the input values through the entire high clock pulse. Another way is to produce a flip-flop that triggers only during the signal transition from 0 to 1 on the clock, and is disabled at all other times, including the duration of the clock pulse. Such a circuit is said to be edge-triggered flip-flop. Edge-triggered flip-flops tend to be faster and have easier design constraints than pulse-triggered flip-flops, so they're much more commonly used. Pictured here is the negative edge-triggered D flip-flop, which is currently the most common flip-flop. Here we see the logic diagram of a D-type positive edge-triggered flip-flop. The flip-flop is an edge-triggered flip-flop, with the sample latch a D latch, and the whole latch an SR latch or sometimes a D latch. Also, an inverter is added to the clock input. Because the sample latch is a D latch, the flip-flop exhibits edge-triggered rather than pulse-triggered behavior. When the clock input is equal to 0, the sample latch is enabled and transparent and follows the D input value. The whole latch is disabled and holds the state of the flip-flop fixed. When the positive edge occurs, the clock's input cycle changes to 1. This disables the sample latch so that its value is fixed and enables the hold latch so that it copies the state of the sample latch. The state of the sample latch is to be copied to the state that is present in the positive edge of the clock. Thus, the behavior appears to be edge-triggered. With the clock input equal to 1, the sample latch is disabled and cannot change, so the state of both the sample and the hold latches remain unchanged. Finally, when the clock input changes from 1 to 0, the sample latch is enabled and begins following the D value. During the 1 to 0 transition, the hold latch is disabled before any change in the sample latch can reach it. Thus, the value stored in the hold latch remains unchanged during the transition. In working with latches and flip-flops, there are some standard graphic symbols for these. In general, we use a rectangular block with the inputs on the left and the outputs on the right. Here we see the symbols for the SR and D latches. Now let's look at the flip-flop symbols. One output designates the normal state of the flip-flop or latch. The other, with the bubble, designates the complement output. The graphic symbols for the SR flip-flop has inputs S and R indicated inside the block. In the case of the SR latch, there are bubbles added to indicate that the setting occurs for zero-level inputs. Graphic symbol for the D latch, or D flip-flop, has inputs D and C indicated inside the block. Below each symbol is a descriptive title, and the hat symbol means positive pulse, and the upside-down hat is negative pulse. For the edge trigger flip-flops, the one going up to down indicates positive edge, and the one going down to up indicates negative edge triggering. Triggering by the 0 level rather than 1 level is denoted on latch symbols by adding a bubble at the triggering input. In contemporary practice, positive or negative edge trigger D flip-flops are the most commonly used flip-flops, so those are the ones you want to worry about. Often, all the flip-flops used in a circuit are of the same triggering type, such as positive edge triggered. All the flip-flops will then change in relation to the same clocking event. Going forward in the textbook, all the flip-flops are of positive edge triggered type, though there may be some exceptions. This provides the uniform graphic symbols for the flip-flops and consistent timing diagrams. Flip-flops often provide special inputs for setting and resetting them asynchronously, that is, independent of the clock. The inputs that asynchronously set the flip-flop are called direct set or preset. The inputs that asynchronously reset the flip-flop are called direct reset or clear. When the power is turned on in a digital system, the state of the flip-flops can be anything. The direct inputs are useful for bringing flip-flops in the digital system into initial state. The function table here specifies the operation of the circuit. The first 3 rows in the table specify the operation of direct inputs S and R. The inputs behave like NAND S0 R0 latch inputs. These latches operate independently of the clock and are therefore asynchronous inputs. The last 2 rows in the function table specify the clocked operation for values of D. The clock at C is shown with the upward arrow to indicate that the flip-flop is positive edge trigger type. The D input effects are controlled by the clock in the usual manner. The textbook focuses heavily on D flip-flops, but there are others. If you'd like to see the details of these, they're covered in Circuit Versus online textbook. SR flip-flops operate with positive clock transitions or negative clock transitions, whereas SR latches operate with an enable signal. The JK flip-flop is a modified version of the SR flip-flop. It operates only with positive clock transitions or negative clock transitions. And finally, the T flip-flop is a simplified version of the JK flip-flop. It's obtained by connecting the same input T0 to both inputs of JK flip-flop. Thanks so much for watching. Be sure to visit La Lima for a